Good day and welcome back to the first part of our discussion on areas. Before jumping into areas, we are going to begin with a detour into sigma notation. And more information related to sigma notation can be found in the back of our course textbook in Appendix E. So to begin, sigma notation allows us to conveniently and very compactly use notation that represents adding together multiple terms that all follow a similar pattern. So for example, if we have a quantity such as am plus 1 plus am plus, I have a small typo here, plus 2 plus ... all the way up to a sub n, how we would represent this in sigma notation is the sum of terms of the form a sub I, where this I represents an index that goes from m up to n. So we substitute in I equals m for the term a sub m, we put a plus sign. We substitute in the next value, m plus 1, we put a plus sign. We substitute in the next value, we put a plus sign. And we follow this pattern until we reach this upper index of n, and that tells us to stop adding up these terms. And to investigate a few more examples, if we wanted to sum from I equals m to n of f sub I, this is telling us we take this general form, f sub I, we substitute in I equals m, we put a plus sign. Then we substitute in m plus 1, and we put a plus sign. And we continue this pattern on until we reach our upper index, so all the way up to plus f of n. We think of this m as being the lower index and n as being the upper index, and those are always going to be whole numbers. Similarly, if we wanted to do something like the sum from I equals 0 to n of a sub I, we follow this same basic idea. We start off by substituting in I equals 0, we put a plus sign. Then we go to I equals 1, we put a plus sign. Then I equals 2, we put a plus sign. And we keep doing this all the way until we reach that upper index, which is an n. So all the way up to adding a sub n. That's when we stop. And we should now practice a few of these examples. So in the first example, we see an expression that involves a sum, and we would like to put this or express it in sigma notation. In the following example, we're given a quantity written in sigma notation, but we would like to write it out so that it does not involve sigma notation. And what I would like you to do is to pause the video and give yourself 2 or 3 minutes to complete these two examples. And at this point, hopefully you've taken a few minutes to work through these examples. And my hope is that sigma notation is something that we've all encountered at some point in the past. It might not be something that we use regularly, or it might even be something we've tried to forget. But when we encounter sigma notation, it's usually from a good perspective. We're trying to write something in a more convenient way to make it easier to understand, or to just save ourselves the hassle or the time to have to write out all of the details. So in this first example, what we're trying to do is express this quantity in sigma notation. So we're going to have some sum, and what we are going to be summing or adding up, we need to represent as a general pattern. And the observation I would like to make, that you hopefully made as well, is that each of these quantities is a number raised to the 4th power. Remember, 1 is equal to 1 to the 4th, plus 2 to the 4th, plus 3 to the 4th, and so on. So we are summing up these quantities that are of the form I to the 4th power. We start off with this lower sum of having I equal to 1, and we continue adding in this fashion until we get to the upper sum where I is equal to 12. So in sigma notation, we have the sum from I equals 1 to 12 of I to the 4th. In this next example, we're doing the opposite thing. We're starting off in sigma notation, and we're trying to rewrite it so that it does not involve sigma notation. And usually this is maybe the easier of the two directions because it's very procedural in a sense. We substitute in n equals j, we put a plus sign. Then we go to n plus 1, we put a plus sign, and we stop when we reach that upper index of n plus 3. So how many terms should this sum involve? 4. Substitute in j equals n, put a plus sign. Substitute in n plus 1, put a plus sign. Substitute in n plus 2, put a plus sign. And then we finish with n plus 3. And when it comes to sigma notation and how we are going to make use of sigma notation in terms of calculating enclosed areas, there are some useful properties or formulas that we are going to need to make use of. And we'll go through these one by one, and I'll add a little bit of explanation in a few spots, but the first few definitely make sense intuitively. If you want to sum up a constant times a sub I, this sum depends upon an index I, so any quantity that does not involve that index I would be considered a constant, and as we've seen many times, we can pull constants out front. So this can be written as the constant c times the sum from I equals m to n of a sub I. And then if we move over to the right, if we're summing a sub I plus b sub I, we can break this sum up over addition. That is to say, we could write it as the sum of the first part, a sub I, plus the sum of the second part, b sub I. And it's also worth observing that if we combine this with the first property, there's nothing stopping us from breaking a sum up over a difference as well as addition. Then moving on, if we were to sum up from I equals 1 to n of 1. And note what this is asking us to do. The quantity we're summing up does not involve I. So regardless of the value we substitute in for I, we always just get a 1. So we substitute in I equals 1, get a 1, we put a plus sign. Substitute in I equals 2, we get a 1, we put a plus sign. And we keep doing this all the way until we get up to n. So what we're really doing in this case is we're adding up 1 n times. So the value of this sum is simply n. And similarly, this next quantity would be c times n. The reason being is if we think about this to the side, the sum from I equals 1 to n of c. Well, c is really c times 1. C is a quantity that does not involve I, so you can pull it out front. And when you pull it out front, you're left with the previous sum, which is just n. The remaining 3 sums are less intuitive, and they actually require one to go through a few details to come up with the formulas. I typically do not go through those details because I don't think they help us with what's to come next. But what I will say is that if you go to Appendix E in the back of the book, you can probably find more details, at least in the first 2 cases, than you may want. But if you do have any questions or want any clarifications as to where these formulas come from, feel free to stop by my office hours or drop me an email. So the first formula, the sum from I equals 1 to n of I, note what this is asking us to add up, just to make sure we're all on the same page. We substitute in I equals 1, we put a plus sign. I equals 2, we put a plus sign. 3, plus sign. And we keep doing this until we reach n. So we're just adding up the first n whole numbers. And what you get when you do that is n times n plus 1 over 2. And this is a formula we will make frequent use of in our upcoming videos for this section. The next quantity, the sum from I equals 1 to n of I squared, it turns out that this is n times n plus 1 times 2n plus 1 over 6. And the final sum, I equals 1 to n of I cubed, is the quantity n times n plus 1 over 2, and that is squared. Now, my silly way of remembering the final 2 is for I cubed, we're taking that formula when I is to the first power, and we're just accounting for those extra 2 powers that we missed out on. And note that's complete nonsense mathematically, but that's how I remember this maybe more intuitively. And then similarly, if I'm trying to remember this formula for the sum of I squared from 1 to n, how I remind myself is I start off with that n times n plus 1 over 2. You need an extra term in the top, which is a 2n plus 1. And there's 3 terms in the top. 3 times that 2 gives you the 6. So it's, once again, nonsensical mathematically, but hopefully it might give you a way to remember this formula. And that completes our current discussion in introduction or a reminder to sigma notation. Remember, you can find plenty of good examples and more discussion in Appendix E in the back of the textbook. In our next video, we are going to begin our transition into enclosed areas and start to investigate what in the world this has to do with sigma notation. So stay tuned and take care.